Welcome to the video on equilibrium of vectors. When you're studying vectors, I hope that you're going to cover the topic of equilibrium. And equilibrium simply means that if you take the sum, so the addition of all the vectors which are being applied, now typically those equilibriums might be something to do with physical structures, and we'll do an example of that. But in terms of just plain mathematics, if you're going to be adding up all of your vectors, then what you will find is that the resultant vector is actually the vector 0. So you can write that out in a summation form, as I did right here, or you can write it directly and you can say, okay, so here are my vectors. So this would have been, for instance, vector 1. Okay, and then this would have been plus vector number 2 and plus, okay, and you can keep going until you sum up all of your vectors, and let's assume that we have n vectors in here, and what you will find is that the resultant vector, so the resultant vector that you have of all of this, is actually equal to 0. So all of the vectors are canceling each other off. And if you can imagine, those points of equilibrium are actually pretty useful to be able to have, because very often we do want equilibrium points. So if you don't want to break your arm or something of that nature, you do want to be stuck in equilibrium where there is an absorption, okay, of your forces, for instance, which might be acting on your arm, okay, or you can talk about, for example, a bridge which you want to be standing in equilibrium. You certainly don't want it to collapse, so it has to withstand a certain amount of forces, and those particular structures are typically referred to as kind of being in static. So static just means non-moving, okay, and dynamic means that it is moving. So in static structures, we do want the summation of all the vectors to be able to sum up to 0. Now, sometimes what you will find is that they may not sum up to 0. So for instance, you can take, okay, a set of vectors, okay, as we did just right here. So for instance, I can take all of these vectors. I'm going to just duplicate this. I'm going to change the color of this as well so that it stands out for us. So let's say that we have this, and we obviously can find the resultant vector in here, but let's say it's not equal to 0, right? So what you would have in here is, let's say you were finding this out, okay, and then you're finding your resultant vector, and maybe it is not equal to 0, okay, to the 0 vector. Well, what do? Well, you're going to have to try to apply or find, okay, a force which would have been an additional force to all of this, okay, so that it equals to 0. But if you already have the resultant vector, then that's actually not very difficult to find, because if all of this is equal to the resultant vector, then all you have to do is you can add an additional vector. So add the vector which is the opposite of your resultant vector, and this, of course, by definition is going to be equal to the 0 vector. So that is something which we can certainly do. And this vector that we have, if you're going to be finding this out, sometimes it is called not the equilibrium vector, although I sometimes like to call it that way, but I think it's called the equilibrant vector. And that particular vector that you have just simply ensures that the summation now with that vector is going to be equal to 0, and that is called the equilibrant vector. Now, where does this come into play, right? So how would you be using this? Here's the example, okay, that I would want to be able to use to kind of go over these concepts of equilibrium, okay, and then finding the equilibrant vector. So here's an athlete, okay, so let's imagine that this athlete has gone through maybe an injury, and so they're lying down, and now they're going to be working on some physiotherapy, for instance, okay, where they're lifting their leg up, but it's being supported also by kind of a pulley to ensure that this leg stays in equilibrium at some particular point. So what we have is, okay, so this athlete or this patient is capable of actually lifting their leg at an upward force of 85 newtons. Okay, so that's what they're capable of. That's kind of their maximum. Now, the leg itself has an estimated mass of 35 kilograms, and for all of you, if you wanted to know, so anytime you have a mass, well, it's always acted on by gravity, and so gravity pulls us back down. So that means that there's a force which we call the weight. Okay, so it's the weight of a person, which we can actually figure out. It's just mass multiplied by the gravity, and gravity is 9.8 meters per second squared. So if you take the mass and you multiply it by g, you're going to get exactly what the weight is. Now, for whatever reason, there's an extra unknown force here. So this particular force, there's a 12 newtons at south 30 degrees west. Okay, so there's that particular angle that we have. And our interest is to find out what force would have to be present in the tension rope to keep the leg in equilibrium. So, you know, we need that particular force, and we also kind of have to angle, you know, at what particular angle, okay, you see there. So there's a question mark that we're going to have to try to find what that is. So how would we relate this back to these equilibrium points? Well, the goal is to be kind of in static, okay, so meaning no motion at all. That's the goal. So we want to be able to find our forces so that they all cancel each other off. So let's try to draw all the possible forces in here, and I'll label them as I'm going through them. So we have a force, okay, so this athlete is capable of kind of an upward force, okay, of 85 newtons. So maybe, you know, let's make this 85 newtons, okay, approximately, and let's call this force F1. So that's going to be upwards, so 85 newtons up. We have the weight itself, so that's going to be 35 times the actual gravity, so 35 times 9.8, so that's 343. So that's going to be downwards. So now, well, let's see, I'm going to maybe, if I make this proportional, it would have been really, really large, but okay, I'll just make it this big. It's not exactly proportional, but that's all right. Okay, so let's say 1, you know, 2. Okay, so give or take, okay, let's say it's approximately this. So this is 343 newtons, and it is down. And then we have this extra additional force right here, so 12 newtons at an angle of 30 degrees west. Well, 12 newtons is tiny, so it's going to be, you know, very small. I'll just put it in like that, okay, for us. And that angle right there is going to be 30 degrees, and this is, let's call this F3. Okay, so that's what we would have there, and that is 12 newtons, okay, at that particular angle. Now, what we are trying to find is, we're trying to find what that force is, okay, that tension, and then what that angle would be in there, so this is all kept in equilibrium. So as you can see here, so obviously it's going to have to be up in some way, and then I guess it's a little bit to the right, okay, so as we're kind of suspending this through, and that's because of this tiny 12 newtons over here. So we're going to have to try to figure out what maybe the resultant force is, and then when we want to keep this in equilibrium, okay, so there's going to be some force probably, you know, somewhere over here, okay, and it's going to go off, and it's going to be probably relatively large, but we'll find out what that will be. Let me just remove this for the moment, and we'll call that force, you know, F4. So this is what we're trying to find in here. Okay. So in order to find this, well, I can do F1 plus F2 plus F3, and that's going to give me the resultant force, so whatever that will be. Let's call this, you know, the resultant force in here. And we want to find the opposite of this resultant force, and that's going to be equal to our F4. And it's going to be with the angle and the magnitude. Well, F1 plus F2 is actually kind of simple because they're in the y direction. So I can take, so 343 minus 85. So in the y direction right here, so this is going to be 258 newtons and that's going to be down. That's just from these two together. Now that F3, I can certainly break that down. So F3 right here. I can break it down into its X component, and I can break it down into its Y component, so I can find out what those are. So notice that's 30 degrees, so that means to the horizontal it's going to be 60 degrees. So the X component is going to be 12 newtons multiplied by, and that's going to be cos of 60, and that's going to be to the left. And I guess cos of 60 is a half, so half times 12 is going to be 6 newtons to the left. And then the Y component of that is going to be 12 newtons multiplied by sine of 60. Well, sine of 60 from the unit circle is going to be square root of 3 over 2. So I guess we're going to have to round this a little bit. So let me just plug it in. 12 times sine of 60. So that's going to be equal to 10. Okay, let's keep it 39 newtons. And it is down, right? So you can see that it's still pointing down right there. So altogether, I can certainly sum these up. So this is what I have from F1 and F2. That's down, and this one is down as well, so I can keep those components together. So if I wanted to, I can have my resultant. So my resultant, this is going to be my Y component. So that's going to be 268.39 newtons, and that's down. And then my X component is going to be just simply 6 newtons left. So that's my resultant. Now, because of the fact that I want to find its opposite, okay, so I can certainly do that. Well, its opposite is not going to be down, right? So this right here, we want to have the same magnitude but up if we want to be able to be in equilibrium, so to cancel things off. And this one, instead of left, is going to be to the right. So we're kind of looking at something like this. So our resultant is this is going to be very puny, right? So 6 newtons, okay? And then this is going to be monstrous, okay? Because it's not really scaled properly. But so this is 268.39, and this is just simply 6 newtons, right? And then my F4 is going to be this, okay? So this is going to be my F4. And we can find out what this angle is. So finding the angle, okay, right there, opposite over adjacent, right? So this is, if I call this angle theta, is equal to, so opposite, 268.39 all over, okay, over adjacent, which is 6. And now using tan inverse, okay, of all of this, put a dot. This is going to be very close to 90. Because of that enormous amount there in the Y direction. So 268.39 divided by 6. I don't know, my guess is close to 90. Yeah. So this is going to be 88 point, let's say 7 degrees. So that's that angle. So there you go. So this question mark right here, so this certainly the way that this pulley is, we would have to kind of shift it over further and further, so it's more so like this, right? That it's pulling this over like that, and that angle would have been 8.7 degrees. So it's almost vertical, which makes sense because this one is so tiny. So that's what we would have there. Now its magnitude, so the magnitude of F4 would have been, well, that's going to be the square root 268.39 squared plus 6 squared equals, yeah, well, definitely is going to be something very close to that. 268.457, it's a fine, so let's just round it, 268, okay, approximately newtons at this angle. And that would have kept this athlete's foot in an equilibrium, and that would have been its angle that we would have to set up that pulley at. And that's an interesting question, right? So it really forces you to say, yeah, these equilibriums do exist. So that F4, which is your equilibrant force, if you sum up now F1, F2, F3, and F4, it's going to be 0. Okay, it's going to stay at equilibrium. All right, so I think that example hopefully illustrates to you where you can utilize these, and it really pushes your understanding of these forces as well, applied to an actual kind of almost like a physics example that you have in here, which is pretty cool, right? Okay, so thanks for watching, and we'll see you in a future video. Okay, bye everybody.